Good afternoon. I'm Tim Weaving. I'm an undergraduate mathematics student at Cardiff University. This talk will outline the RSA algorithm and consequently delve into its mathematical foundations. Our modern era is very much led by technology and driven by technology, with so much of what we do on a day-to-day basis being reliant upon the transfer of data in some way. How can we be confident that such data is secure and not prone to malicious attack? Pictured here are Rivest, Shamir, and Edelman, the three founding members of the RSA crypto system. RSA is an example of what we call an asymmetric crypto system. Within a symmetric crypto system, we have a single key which deals with both the encryption and decryption of some data. If, for example, I wanted to communicate with someone, I would in advance have to agree with them what this key would be, which in itself has its shortfalls. Say I wanted to communicate with someone on the other side of the world, short of meeting them in person, which is impractical. I have to somehow transmit the knowledge of my key, which in itself is not immune to prying eyes. So now where an asymmetric system differs is in that there are two keys which are related to each other in some secret way. One key is used to encrypt and one key is used to decrypt some data. The decryption key I can keep private to myself, and the encryption key I can allow to be publicly available. This is kind of like handing out a bunch of open locks. Anyone can grab a lock and secure a bit of information, but then only I with the private key can then unlock that information again. This is all well and good, but how exactly do we produce two such keys which have the required properties that they are each other's inverse, but also one is nearly impossible to infer from the other? Well, this is exactly the RSA method. On the screen now is an overview of the RSA algorithm, which bits of it may seem alien at this point to the less mathematically inclined, but we will slowly dissect it throughout this talk. I apologize in advance, we're now going to do a little bit of number theory. Some of this might seem entirely obvious and unnecessary, such as the first bit there, but I think it's important that we rigorously define these concepts before building more complex structures such as RSA on their foundation. Firstly, it's important that we're aware that any number n can be expressed as a unique product of prime numbers. This is known as the fundamental theorem of arithmetic. Secondly, we'll be making use of the greatest common divisor function, which takes two numbers, say a and b, and returns to us the largest number which divides both a and b, which we will denote by GCD of a and b. At this point, I'll also introduce a little bit of terminology. We'll call two numbers coprime if their GCD is 1, or in other words, they share no common factors. We'll also have to familiarize ourselves with a little bit of modular arithmetic. If I were to ask what 9 add 5 was, I don't think anyone would hesitate to say 14, and you'd be perfectly right, but this isn't necessarily always the case. For example, addition on a clock face. 9 and 5 is in fact 2, since clocks run modulo 12. The notation we use for this is the congruence notation, denoted by the three horizontal lines, and that simply reads as A is congruent to R mod n, or in other words, a remainder of R is left when we divide A by n, or equivalently, A mod n is equal to R. This is all well and good, but how do we get a computer to calculate something like a GCD? So this is where the Euclidean algorithm comes in. What this does essentially is it takes two numbers a and b, replaces a with b, and then replaces b with a mod b, which we'll call, say, R1 for now. And then we iterate this. We replace b with R1, replace R1 with b mod R1, and we do this as many times as is necessary. And then, so this algorithm will always bottom out and reach 0 eventually. It turns out that the penultimate number is in fact the GCD of A and B, which can be shown mathematically, but that's not something I'm going to do in this talk. So we can now extend the Euclidean algorithm a little bit to do a bit more for us. It's true that given any a and b, we can always find some solution x and y to the equation ax plus by is equal to d, where d is the greatest common divisor of a and b. What the extended Euclidean algorithm does is it finds us one such solution of this equation. At the moment, it's probably entirely not obvious why we'd want to know that, but it will crop up a bit later on in the RSA algorithm. And so here is just some very simple Python which runs both of those two algorithms. You'll see in the first one it's simply replacing a and b with b and a modulo b, as was outlined. So some of the more eagle-eyed, I hope you may have noticed what looks suspiciously like an identity matrix in the extended Euclidean algorithm, and you'd be right, since all the extended Euclidean algorithm is doing is a little bit of linear algebra alongside the standard Euclidean algorithm. This is my favorite bit of the RSA algorithm, is Euler's Totient Function, denoted by the Greek letter phi. What the function does is it counts how many numbers less than, say, n are co-primed n, so how many numbers less than n share no common factors with n. The function itself might seem a little daunting, but fortunately, due to a mathematical property of the function, we need not actually use it in its entirety, since when a and b are co-prime, the totient function of their product AB is simply the product of their totient functions, 5a times 5b. So within the RSA algorithm, what we're doing is we're taking two prime numbers p and q and multiplying them together. So clearly we can use this as p and q must be co-prime since they are each other both prime. So the totient function of n, which makes up part of our public key, is just the product of phi of p times phi of q. Where the function gets really interesting, though, is when we actually plot it. When I first naively plotted the function, I had no idea what to expect, but it certainly wasn't this. You see there's distinct lines appearing in the points. And if instead we plot phi of n, we plot phi of n over n, we get the lines constant at particular values and are very clear. It took me quite a while to realise why this actually was, and it's one of those moments where it kind of kicks you, and you realise that there was obviously no other way it could have been. But I invite anyone to have a look at, think about why it might be. Feel free to talk to me or ask at the end if we have any time for questions. Why that is. Here's a clue if anyone wants to have a think about it. I've got no more, I'm afraid. Okay, but that's a bit off topic. We'll return to the RSA algorithm. If anyone does want me to talk about it at the end, then I can do. So we picked two prime numbers p and q, and I should mention at this point that these aren't like 11 and 17. These are huge numbers. Current RSA keys are 1024 to 2048 bit numbers, which are 300 to 600 digits long, which is where the strength of RSA lies, in that factoring such huge numbers requires huge amounts of computational effort, which take literally centuries, even for the best of computers to compute. Once we have n, we then need the totient function of n, which, due to the property which we outlined earlier, is just p minus 1 times q minus 1, since the totient function of a prime number is 1 less than the prime number, because all numbers less than the prime number are co-prime to it. Okay, so that's the first step of the RSA algorithm. Now we need to find some number e, which is co-prime to the totient function of n. The way that I do this, anyway, is just let Python produce a random value for e, then increment e until we arrive at some such number which is co-prime to the totient function of n. Once we have e, we now need to find some number d, which is such that its product with e is congruent to 1 mod phi of n, or in other words, de divided by phi of n leaves a remainder of 1. This is where the extended Euclidean algorithm comes in, because it turns out that the p coefficient of the equation is one such d as we require for this part of the algorithm, which again can be shown mathematically, but I don't think I'll be doing. Okay. So we now have everything for our public and private key. We make N and E publicly available, and we keep P, Q, and D private. How now, though, do we go about actually encrypting some data? Clearly, if you want to transmit some text, you need to convert it into, say, like numerical ASCII characters, so that we can perform mathematical operations on it. And then we make use of Python's POW function, which takes 3 arguments, x, y, and z, and returns x to the power of y mod z. It doesn't do so in the standard modulo way. It makes use of modular exponentiation to very efficiently do this to huge numbers like are involved in RSA. So we take some plain text, say m, and we raise it to the power of e, which is publicly available, and we put the whole thing modulo n. This yields our ciphertext C, and that's all you do to encrypt the text. Then, so we want to decrypt it. It's a very similar process. We then take the ciphertext, raise it to the power of D, which is a private part of the private key, and then again put the whole thing modulo n. And that is the outline of the RSA algorithm. Just have a brief demonstration as well in Python of that. And it's in 2 screens, so it's not coming up. Yeah, there we go. Okay. It's just some pretty basic Python. So first, it's just the converter from ASCII to text. Here's the extended Euclidean algorithm, which we went over just now. And then this carries out the main body of the algorithm. It just takes 2 prime numbers, multiplies them together, and yeah. So for this, I just picked 2 large prime numbers. These still aren't anything like the sorts of prime numbers which are actually involved in RSA. But an actual RSA algorithm will generate these prime numbers themselves, which I couldn't figure out how to do. So we'll run that. Does anyone have any suggestion as to anything they might want to encrypt?
Hello world.
Ooh. I might need some help with that one. Oh, how's that spelled? P-O-R-E. Oh, D-A.
Yeah, and then letter Y is a new word. Yeah, just a letter Y is a
Oh, sorry.
yeah, but separate from the and a new word again, B-Y-D.
D-Y-D. Yep. Okay. We run that. It converts that into plain text as a numerical plain text, encrypts that to ciphertext, and then below the scored line, decrypts the text again. It is indeed the same as the text we started with, and there's the final message returned. Thank you. Yeah, that's all.
Great. Does anyone have any questions for Tim?
I'll try and answer some.
Can you stand up, please?
Can we have another clue, please?
How much time is?
You've got time.
Or maybe someone in the audience. I think you didn't want to give it away, obviously, because there might be a few budding mathematicians who know why those lines were appearing on the graph. Anyone? Oh,
The top line is the primes.
Yep.
And then there's primes times 2 somewhere, and then primes times 3, and so on. We'll give the other increasingly more sparse lines.
Yeah, you're on the right sort of track. If you actually look at the function itself, I'll briefly explain what it's doing. So the totient function of n. So it's n times, and this big symbol here is simply the product symbol. So what it does is here the P and then the partition N, it just means this product is taken over the unique prime factors of N. And so then we multiply 1 minus 1 over P for each prime, a unique prime within N, times it by N. So when we plot 5N over N, all we're getting is this product thing here. And all that is essentially it's just the product of P minus 1 over P. So if I go to this one here, so the points are colored such that each point is colored with the lowest prime, unique prime within its product. So if a number has has 2 as one of its prime factors, then it's colored red. If its lowest prime factor is 3, it's colored orange. So within this function, if a number has a 2 within its prime factorization, its totient function is immediately halved. So it's less than or equal to half, which is why we see this line appearing at 0.5, because all numbers which have a 2 in its product will be below that line. And then with 3, instead of getting, we get now this line appearing at 2 over 3, it's always 1 less than a prime over the prime itself, due to how the function, due to how this function works. And you also see that underneath the 0.5 line, that same pattern kind of repeats itself underneath. There's a kind of fractal nature to it. This is because after you have you get rid of the 2, then the next largest prime is 3, and so you get it repeating beneath. And that's kind of a bit of a sketchy explanation of what's actually happening, but I hope it kind of makes sense.
Any other questions?
Some people who wear tinfoil on their head have told me there are problems with the RSA algorithm. Are there, and should I be worried?
I have heard of some problems to do with RSA. And actually, I think a lot of the time in the real world, people will actually use a symmetric crypto system, but use something like an asymmetric system like RSA to encrypt the key that you're using for the symmetric system. And so all of the heavy encryption is done using the symmetric system, but the actual keys themselves are transmitted using RSA. As per the issues with RSA itself, I'm not entirely sure exactly what they are. But yeah, last night I was frantically trying to find out just in case someone asks, but I'm afraid I don't know.
Most cryptographers recommend the use of RSA, or do they recommend the use of some other asymmetric crypto system?
I'm not actually entirely sure. I'm not a cryptographer myself. There are many other examples of this. There's elliptic curve cryptography, which is another example. But I'm not sure what a cryptographer would say was a preferable means of encrypting something, I'm afraid.
Great. Let's thank Tim one more time.
Thank you.